packet, or you're getting very close to going into your next packet. Yeah. So for those of you who don't have hole punches, there were 2 packets, and I think we're getting ready to head into the second one here. So if you had hole punches, I gave it to y'all at one time because the copy machine can handle that. It just can't handle the saddle stitch. They call it a saddle stitch when it's in the middle like that. All right, solutions and mixtures. I think solubility might be next, or might be tomorrow. Okay, Wednesday. What are we doing tomorrow? Quiz?
I should hope not. Oh, no, maybe it is tomorrow. And then it's also Wednesday.
So solubility is 2 days?
So solubility.
We don't have a quiz coming up?
Solutions and mixtures.
I think we were supposed to have a quiz today.
Oh, okay. Quiz was supposed to be today. We'll do the quiz tomorrow then. Okay.
Oh my gosh, thank you so much.
Well, I screwed that up. I'm sorry, guys. I know you're probably very disappointed in not having a quiz today on a Monday after a weekend. But yeah, we'll do the quiz tomorrow and do the notes today. Okay. Okay. Solutions. Solutions come in the form of solids, liquids, and gases whose macroscopic properties vary due to the fact of the composition throughout. I was just, and this is going to bop me out of here. It does it every day. I was just looking over the labs for honors this weekend, and many of them were telling me that solutions were in a single phase. And that's not true because you've got, think about pop, for example. Okay. You've got a liquid, but you have carbon dioxide dissolved in there. That's 2 different phases. The oxygen that's dissolved in the water that the fish use for respiration, that's 2 different phases. Okay. So I marked all of those wrong all weekend long because they obviously didn't spend any time looking at properties and that sort of thing. They found it on some Google site, thought that it was right, and just wrote it down and didn't really think about it, even though we've talked about pop and we've talked about these other things. But if you think about it, there are 2 different phases there, and that's a good example of that. Okay. The only formula that we really use when we're talking about solutions in here is molarity. Okay. We do mole fractions too, but that's a little different. You can do mole fractions with anything. So back in the day when you had regular chem, we did 5 different things. Okay. Remember molality? So we have molality and molarity. So the moles of solute divided by the liters of solution. When you see the little n here, you should be getting used to recognizing that as moles. Okay, you had that in the ideal gas law. PV equals nRT. The n is moles. All right. For liquid solutions, the solute may be a gas, liquid, or solid. While there are many different methods for describing solution concentration, molarity is the one that we use most of the time. All right, components cannot be separated by using filtration. The particles are too fine. Okay, so we don't have filter paper that's possible of doing that. And I talked to Mr. Schramm about that last week, and he said, there's filters out there that get really fine, but nothing that would filter this stuff out. There are no components large enough to scatter visible light. If you remember the Tyndall effect, if you remember us talking about that, how if you have a colloid such as fog and you shine a light through it, it's going to reflect the light back or refract it. That's why they tell you not to use your high beams in fog, because fog, it's just going to refract it back into your eyes and make it worse, not better. Components can be separated using processes that result in intermolecular interactions among the components, such as distillation. So distillation is where you are going to use the boiling point of the smaller, or the thing that has the lower boiling point, weaker IMFs. You're going to boil that away and then be left with the material behind that has a higher boiling point or higher IMFs. They do that a lot of times. They'll use that for desalinization of salt water. That is also how they do most of your grain alcohols that people over 21 are allowed to purchase and consume. And then it's also a common way that they will purify crude oil. So when crude oil comes out of the ground, there's a bunch of different types of things in there. It's not just plain oil like you would shove into your motor. Okay. There's a bunch of different components in that, and they will heat different ones and boil different ones off and collect them. And that's what a refinery does. And then chromatography, we're going to get into that towards the end here, I think towards the end today. And that takes advantage of different polarities of the substances. Okay. Ion concentration, then ionic compounds dissociate into ions when they form solutions. Because of that, the concentration of the ions in the solutions are given may not be the same as the original formula. For example, 1 mole of sodium chloride will dissolve in water to form 1 mole of sodium ions and 1 mole of chloride ions. But if you have calcium chloride, you're going to get 2 chlorines for every 1 calcium. So you will end up with 2 moles of chlorine in that case. Does that make sense? CaCl2.
Happy Monday, Libby.
Why? Nope. Okay. Yep. Happy Monday. All right. Well, you'll just have to imagine that I'm doing the thing splitting apart there then. I don't know what else to do. All right. Sorry. Yeah, this is good. We saw in Unit 1 that our solution can be expressed in terms of moles of a solute per liters of solution, which is called molarity. We've done that before. Low molarity solutions, there's very few solute particles and a lot of solvent particles. And then in high molarity solutions, you've got a relatively large amount of solute compared to the solvent. Okay. We call the low molarity solutions dilute. So if something is very dilute, that means that it is has a low molarity. What do we call the high molarity solutions? Concentrated. Yep. Okay. All right. We've talked about dilution. We did serial dilution back in Honors Chem, if you did that class. That was the one where we had all of the copper sulfate solutions up here. We had really dark ones all the way to super light. Kind of a spectrum there. And when you're doing these, you're going to have 3 different steps. You're going to calculate the moles present in the final, the moles in the dilute, and then you're going to end up multiplying that by the volume. Okay. So final solution has to be 2 liters, and we want the molarity to be 3 molar. If you see moles over a liter, you can think of that as a capital M. That is the units for molarity. Okay. And then that we want to have 6 moles of KOH, and you have to figure out how much KOH you need to be able to supply that. Okay. So if you're given the choice of glassware to use for doing a cereal dilution, to be able to measure out the amounts that you want to pick the most precise glassware available. Okay, so if you have a volumetric pipette, that is what you want to use. If you don't have one of those, but you have a burette, then that's what you want to use. If you don't have one of those and you have a graduated cylinder, then that's what you want to use. So in level of accuracy, your volumetric pipettes, okay, those are the real skinny ones with the bulbs. Everybody's used the bulbs before, where you put it on there and you suck the stuff up, I hope. Okay, so choose that. Don't have that, you're going to choose a burette. That's the really tall thing with the stop cock that you got to move around. And then everybody knows what a graduated cylinder is. All right, and this just goes through the steps of doing that. I think everybody's had the opportunity to do it. You've got your burette here. You have your burette clamp. This is what one of those volumetric flasks looks like. This is what you're going to actually do the cereal dilution in. So you would measure out using your burette or using your volumetric pipette. You would measure out your stock solution. You're going to transfer that into the volumetric pipette, or volumetric flask, excuse me. And that volumetric flask has to be the size that you want to end with. So if you want 1 liter of material, this is the volumetric flask that you would want to use. You're going to put that stock solution in here, and then you're going to fill this the rest of the way up until it meets that etched line. The meniscus of it meets the etched line. You can't just say, okay, I needed to add 200 milliliters of my stock solution in here. I'm going to add 800 milliliters of water. Okay, it doesn't work that way, because sometimes those particles will fit closer together, and you'll actually end up, even though you added 800 mils, some of that solute is mixed in there finer, and it doesn't take as much space up. You following me?
Yes.
Is this making sense? Okay, so you have to say you're going to fill it up the rest of the way with water until it meets the etched line. Do not say, I'm going to fill it with 800 milliliters of water, because you might use more water than that. Okay, and it seems like you're being less precise by doing that, but in reality, you're using the glassware properly. Okay, it seems counterintuitive to say that, to not put down exactly how much water you're putting in, but it's irrelevant. You want to fill it to the etched line. The meniscus, you have to say the meniscus, the bottom of the meniscus reaches the etched line. Good? All right. When you're doing these, it's often you're combining that water and the acid. It's very exothermic. Okay? What that means is it's going to release a lot of heat energy. You can get to the point where it is significant enough that it's going to turn it into steam. And if you're talking about diluting down acids and you're now breathing in acids, it can be detrimental. Okay. First few years we had to share classrooms because the population of the school was so much bigger. And I was trying to prep a lab in the back, and I'm like, I'll just dilute this hydrochloric down back here. It'll be fine in the back without a hood. I had to walk out. I had to wait until it dissipated. It was bad, you guys, bad. So I always do that under the hood now. The other thing is it can sometimes be so exothermic. These volumetric flasks that we have, they're not designed really to be heated. Okay. So the glass is not strong enough to handle that heat. You can actually crack these volumetric flasks from the heat involved in this. So oftentimes when we're doing like sulfuric acid, which has a really high molarity, it's 18 molar, and we're dissolving that, or we're diluting that down, we actually have to go and get ice from the training room and do an ice bath with the flask because it's generating so much heat. So you've got to be really careful with these, especially with some of those concentrated acids and bases. All right, calculate the volume of 1.25 molar lithium chloride that can be made with 13.3 grams of lithium chloride. So go ahead and see if you can get that set up and get that to working. I'm going to see if I can figure out some miracle of God way to write on this darn thing. Okay, I can write on my scratch pad then. All right. So let's see here. We've got, this is upside down. That's part of my problem. All right, so I've got to first of all turn this into moles, right? So I'm going to do 13.3 grams. I need to turn that into moles. I'm going to divide by the mass of lithium chloride, molar mass of lithium chloride. Molar mass of lithium chloride then is 42.4. And that's grams per mole, right? So this gram will cancel. That's going to leave us with moles. And that's going to give us our mole amount here. So I ended up with 0.314 moles. Of lithium chloride. All right. Now, that over X moles per liter is going to be equal to what value? 1.25 molar. Yep. And you can think of that as moles per liter if you'd like. All right. Now, if we want to solve for X, X is going to equal 0.314 moles lithium chloride over 1.25 moles per liter. My moles cancel, and that's going to leave me with 0.251 liters. All right. Handwriting isn't pretty on there, but it's better than nothing, I guess. All right. Makes sense? All right. What would the concentration of chloride ions in a solution that is made by dissolving? I hope yours went on further than mine did here.
Dissolving 10.
Okay, in zinc, ZnCl2. Okay. Is that it? And we have a final volume of 500 milliliters. Now, when you're working with molarity, oftentimes it's easier to go ahead and do this, right? So go ahead and get it into liters so that your brain is working well. All right, so we've got 10 grams of zinc, and we're looking at the chloride ion. Okay, So we're going to use our beautiful dimensional analysis, right? Got our zinc chloride here. We are going to take that. Oh. Control Z isn't it working? Nope, that's not working either. Okay, well, I guess we're just going to have to live with that line then. Sorry. So I'm going to take that. I've got 10 grams here. I want to get rid of grams, and I'm going to go into moles. But that's going to be moles of ZnCl2. Okay. And I'm going to use the molar mass here for zinc chloride, which is 136.3, right? Yeah, 136.3. And that's in every 1 mole of this. For every 1 mole of ZnCl2, I have how many moles of chlorine ions? 2. I get that from the formula right here. Okay. So that's going to tell me how many moles of chlorine ions I have. And when I do the math there, I get 0.147 moles of Cl ions. So now if I take those moles and I divide by my volume, and it has to be in liters, you guys, you got to get that thing into liters. That's why I went ahead and did it as part of the problem here. I'm going to end up with 0.294, and that's going to be a capital M, and that's going to be Cl minus ions. Good? All right. You need that back?
No, I'll be all right.
I can get back to it. Work on the we do. Your seat, buddy. There's 2 we do's there. I'm glad they made this a lot easier to work with. Glad they got us new stuff so that it's easier to work with. I was so excited because I got my new HDMI cable and I wasn't having to like climb over the stupid thing, and now the ink doesn't work. All right.
Yeah. I'm pretty sure that we just moved that. No.
So to go from milliliters to liters, you're going to move it 3 spots. So if this is 250 milliliters, we move it 3 spots. It's going to come over here, and that'll make it into liters then. Okay. So when you solve for this, you're getting it into moles. They did not want moles, they wanted grams. So we need to take this, and you can put it back in your dimensional analysis if you're so inclined. If you're able to do that in your head already, then that's fine too. Molar mass for KOH is 56.1. I'm going to multiply across, and I end up with 1.40, and that is going to be grams of KOH. And actually, it should probably be just 1.4 because we've got 2 sig figs here. I should only really have 2 sig figs in my answer. I would erase that, but this thing isn't allowing me to do that. So, but at least I can write. I'll take that at least. All right, questions on that guy? All right, work on the next one then. They will typically give you formulas for stuff. They expect you to already know how to do that. So you don't have to worry so much about the formula, like remembering all that stuff as much. Once you're into AP.
Because how did you just do the situation? I found it.
Yeah, I didn't have to see them.
That's the that should be the moles of answer. Yeah. She goes
That's my answer.
All right, so Chase doesn't understand Stoic. I have my grams here, right?
I think I did it right, actually.
I want to get rid of grams. So I found the molar mass of MgNO3. So I put that on the opposite side. Okay. And that's going to take me into moles. I'm then going to take my moles of MgNO3 too and convert that into just moles of nitrate ion. So for every one of these, I have 2 of these. Does that make sense? All right. So I end up with 0.337 moles of the nitrate ions. I need to figure out the molarity because they're asking for concentration. So we want molarity here. What's wrong?
I got a 0.0337.
0.0. Oh yeah, there is a 0 in there. Thank you, Maddie. All right. Sorry, it's Monday. All right, I'm going to have that over my liters. I just moved the decimal point 3 spots and turned this into liters. So that's down here. And so I end up with my molarity as 0.337 molar, NO3 minus. Yay or nay? Okay. All right, moving on to 3.8, representations of solutions. There's no way I can do this without drawing on the screen. I'm glad I brought this thing over. I'm glad this is at least working. All right, essentially what this is particle diagrams. They love particle diagrams on the AP exam. Okay, they want you to kind of be able to think of this stuff in terms of teeny tiny pieces. What's going on the microscopic level. You good, Haley? Mm-hmm. All right, so intermolecular forces. We talked about these intermolecular forces. We're now going to talk about them in terms of how this relates to forming a solution. Okay. This ion dipole is one that they're going to talk about a lot when we talk about solutions. Okay. The idea that something is soluble is the idea that the attraction between water and whatever ion that is greater than the attraction between the water molecules to themselves or the attraction of the ion, the negative ion to the positive ion, the cation to the anion. Okay? If that's the case, then it's soluble. If it's like silver chloride, for example. If you have silver chloride, it's arranged in this repeating pattern that you see with all of your ionic solids. When you come across this guy, and this happens a lot of times with metals with higher molecular mass, so leads and stuff like that. When you have this, the attraction between these ions is stronger than the pull of the water to pull that apart. Okay, so intermolecular forces exist between the solute particle and between the solvent particle and between the solute and the solvent. Depending on the particular solute and solvent, they either promote or prevent the formation of solutions. And when we get into Unit 7, we actually do math to determine this. So there's actually math that we can do to determine if something's going to be soluble or not. It has to do with equilibrium. Piece of junk. I hate this stupid thing. All right. So the tendency to mix is strong, but if the solvent to solvent and solute to solute attractions are strong compared to those, you're not going to form a solution. The term miscibility, then describes the ability of two substances to mix without separating. Similar materials are miscible in each other, or like dissolves like, but do not write down like dissolves like on your test. You have to be able to describe it in terms of interactions. They will mark it wrong if you just put that down as an explanation. That is not an explanation. That is kind of something that you've observed, but it's not an explanation for why it happens. You've got to talk about polarity here. So typically polar solvents will dissolve in polar solutes, and nonpolar solvents will dissolve in nonpolar solutes. We talked about Red Rover the other day. Okay. And so if you've got something that is polar, it'll typically let things in. But if you've got a polar solvent and you're trying to put a nonpolar solute in there, the attraction to that nonpolar is not strong enough to pull the water apart to let it in. That's oil and water, for example. That's why oil and water don't mix. It doesn't have to do with the density that they don't mix. That's what most people say is the explanation. They say that oil and water don't mix because of density. Well, salt's more dense than water, but it still dissolves. So that's not really a valid claim. Okay. It has to do with the polarity, the fact that water is polar and oil is not. Okay. When you are doing these particle diagrams, you need to make sure that you have your water ends turned the right direction. It's just not advancing now. Nothing. I'm just completely frozen up now. There we go. All right. So if you had this, for example, they might ask you which one's more dilute. Okay, so this one would be more dilute. And they might just give you these numbers here, give you a drawing like this. So maybe they just give you this drawing down here. They give you the molarity down here, and they give you the molarity up here. You have to draw this. You would make sure that if there was 2 chlorines here and your molarity is twice as much, that when you come up here, now you have 4 chlorines. Does that make sense? So that's one of the things that they're looking for. All right. Which solvent would be most effective dissolving the following solutes? Hexane. Hexane is polar or nonpolar? Nonpolar. Yeah. It's just 6 carbons repeated with hydrogens around it, all surrounding it all the way around. So it's going to be nonpolar. This guy, though, water, you know that is polar. Yes, it has 2 lone pairs of electrons here. So there's your water. This guy here is going to be polar. It's got hydrogen bonding. It's going to be right there. So let me just draw him out. I'm going to have 5. So 1, 2, 3, 4, 5 hydrogens here. Now, typically when you see a formula that's given to you that has this OH at the end, that means that you're going to have an oxygen coming off and you're going to have a hydrogen attached to it. Okay. This is known as I can't remember my terminology yet. It's a group. I think it's an alcohol group is what it's called, but I'd have to look it up to verify. At any rate, you're going to have hydrogen bonding here. Remember, when we have hydrogen bonding, we have to be on the phone, which we are. We have to have a hydrogen attached to it, and we need to have lone pairs of electrons on the fluorine, oxygen, or nitrogen, which we do. So that's going to make this oxygen right here very electronegative. Okay, we're going to have a negative pole here. So when you draw this, you need to show that your hydrogens are lined up on that side. You would not want to draw this where this is flipped around and you would have the oxygens coming together here, because the positive end of this water needs to be attracted to the negative end of the ethanol. Does that make sense?
Mm-hmm.
I got another I do. Okay. right, potassium chloride then. We've got a potassium and we've got a chlorine, and we're showing the solubility in water here. So I'm going to put my potassium down here. It is a positive ion. So when I draw this out, I'm going to put the negative end of the water attracted to that. Okay, and then I've got to draw my chlorine over here. And this time I'm going to have my positive end attracted to the chlorine. It's hard to draw sideways. All right, so that's what that looks like. So those are particle diagrams. You're going to go home tonight. You're going to watch the We Do video on this. Okay, you're going to do 3, 7, and 3, 8 tonight. Tomorrow you're going to come in. We're going to do the quiz, and then I'm going to lecture on 3, 9. Okay? I think it's 3, 1 to 3, 6, but if you look at the front of your packet, it should tell you. Well, it was supposed to be given before 3, 7, so it has to be 3, 1 to 3, 6. So.